Hello and welcome. Today we'll be getting into 3.4 on applications. This is for quadratic. So suppose x represents the number of TI-84s sold. By the demand equation, x, the number they can sell in a certain region, is 16,000 minus 160p. And we're going to do a few things with this demand equation. So we'll start by finding a revenue model. So revenue R is just how many we sell times the price we sell them. So P is going to be our unit price, unless otherwise stated. That's going to be assumed to be in dollars. So however many sell times the price you sell them at. So that's not talking about profit, that's just money coming in. Profit also would take cost into account. We can see we're in two variables at the moment, so we can do a little bit of substitution to knock this down to a single variable. And let's see, we'll pick in terms of P. WRT with respect to P. So that means we want to get rid of X. If they wanted it with respect to X, we would have to solve for P. Since we want to get rid of the X and they have X by itself, just a little substitution. 16,000 minus 160p times P. So R of P, negative 160p squared plus 16,000p. Now, as far as the domain of R, we know two things. We know that the number sold is at least 0, and we know that the price, some books will say at least 0 for the price, some will say strictly greater than 0, since they're going to assume the company is not going to give it away. Excuse me. Now, at the moment, R is written in terms of price P, so we can do a little bit of subbing in on that. So our demand equation says that X is the same as 16,000 minus 160 times P, so that's at least 0. So 16,000 is at least 160 times P, so P then is less than or equal to 100 then. So P is also greater than 0, so our domain would be 0 to 100. Now they may also ask us to maximize revenue. Now, since this is quadratic, we know that maxes and mins of quadratics happen at the vertex. As you'll recall from our last test, the vertex is at opposite of b over 2a, and then f of opposite of b over 2a. So for this one, P is equal to, instead of X is equal to opposite of B over 2A, so opposite of 16,000 over 2 times negative 160. So negative 16,000 over negative 320. So we get negative, or positive 50, sorry. Two negatives wipe each other out. So this is the price that would maximize the revenue. They may also ask you to find the maximum revenue. So for that one, we simply plug in our value, R of, in this case, 50, negative 160 by 50 squared, minus 16,000 times 50. So plugging and checking on that, negative 160 by 50 squared, minus 16,000 by 50. Plus 16,000 B, my apologies, plus 16,000 B. So R of 50 lands us at 400,000. So max revenue is, and this is in dollars, $400,000. All right, so the next problem we'll take a look at, we'll work on building a fence around an enclosure, or making an enclosure. So suppose we have 300 yards of fence. So we want to know what are the dimensions of a rectangle that will maximize the area enclosed by our 300 yards of fence. So this one, again, quadratic. So area of a rectangle is just length times width. Our limiting factor here is the perimeter. Perimeter is twice the length plus twice the width. And we have a number for the perimeter. Max perimeter, 300. So 300 is 2L plus 2W. You can divide both sides through by 2. Again, that's both sides, not one big line with a 2 in the middle. I don't know where that bizarre notation has come from. 150 is L plus W, and then we just pick one and solve for it. My W's are easier to read than my L's, So we'll get the L alone, and 150 minus W is L. So then our area by substitution is 150 minus W times W. So A is negative W squared plus 150W. So we want to maximize this. So again, those happen at the vertex. So our vertex opposite of B over 2 times A. So a width of 75. And our length then, we just sub in. So the dimensions to maximize area, assuming that we're following the rule of making a rectangle. If we really wanted to make the most area with the material, we'd make a circle instead. So 75, and our units would be yards. Now, occasionally we do have other limiting factors. So we may be making, say, pens by a river. So here's some of my lovely artwork. Here is a river, and we'll assume that we don't want to put a fence on the riverside, but we want to make, let's say, 4 pens of equal dimensions. So there's 1 pen, 2 pens, 3 pens, 4 pens of equal dimension. And let's say this time we have 1,200 yards of fence to work with. So we want to figure out the dimensions that will maximize the area. So we'll call this our depth and this one our width. So the area, we'll get some variables involved here. We'll make the depth our x, and the width of each one will be a y. Area would be x by 4y, or just 4xy. And our perimeter, loosely the perimeter, not strictly speaking perimeter, since we're not enclosing the riverside, but just how much fencing that we're using. 1, 2, 3, 4, 5 of the x's plus 4 of the y's. So 1,200 yards altogether is 5x plus 4y. And we'll pick one of those to get by itself. Let's say the y. So 1,200 minus 5x is worth 4y. So y is 300 minus 5/4 of x. So then our area becomes 4 times x times 300 minus 5/4 of x. So our area then, 1,200x minus 5x squared. If you'd like to see the squared first, you're certainly welcome to apply the commutative property of addition. So our vertex for this guy is happening at opposite of b over 2a again. And we saw before how that is derived. So negative 1200 over negative 10 is positive 120. And then we can get our width of each pen as well. So just plugging in what we know. So we can just go y is 300 minus 5/4 of 120. It's 300 minus, let's see, 30 by 5, 150, 150. So each pen will be, X was 120 yards deep and 150 yards wide. They could also ask us to maximize that area. That's then just plugging in what we know as far as finding what that maximum area is. So these are the dimensions that would maximize the area. Find the max area, we just do x by 4y. All right. So I did want to run through one more, and this is sort of similar to the work we've done before with our linear equations based off of data. Only the quadratics, the only thing I would recommend is make sure you're going out 4 decimal places or your model gets too far away. When you are squaring something and you have an error in it, the error gets much bigger, much faster than it does when you're working with linears. So we'll work with our speed. That'll be our x, and our miles per gallon, that will be our output, our y value. So car number 1, 30 miles per hour, it's getting 18 miles per gallon at that speed. 35 miles per hour, 20 miles per gallon, and so on. So we'll create this little chart. So 40 and 23, and here's where we'll do the sort of the magic of video, and I'll let you just pause it when I have the completed one up. And poof, there they appear. So you can go ahead and pause that and get the numbers down. And we want to build a quadratic model describing the relationship between the speed and miles per gallon. So we input the data the same way that we did when we had a linear relationship. You can hopefully see that this is nonlinear. Our speed was sort of going up or staying flat the whole time. It was never decreasing. However, our miles per gallon increase, 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 decrease, decrease, decrease. So we go into our lovely little stats menu like before, edit like before. If you have old data in there, you want to clear it. You don't want to delete your list. You want to clear the list. So then we're just keying them in. So 35, 30, 35, 40, 40, and so on. 45, 50, 55, 60, 65, 65 again, and 70. So you should have 11 pieces of data when you're done. And you can see here in the bottom corner We have the little 12 on there is on the blank spot. So then we go over to line 2, list number 2, and enter our miles per gallon. So 18, 20, 23, 25, 25, 28, 30, 29, 26, 25, and 25. So your data should match in dimensions. So if you accidentally keyed in one extra piece of data or omitted one piece of data and you try to calculate something, you'll get a dimension mismatch error when you go to find your function. So back to our stats menu. Again, that's right here below your delete key. We're going to calculate, only this time we know it's nonlinear, so we are going to try a quadratic regression. That is option number 5. Hit enter twice, it'll default to working with list 1 and list 2. And it will give us our coefficients. Again, a reminder, on quadratics you want 4 decimal places of accuracy. So f of x, negative 0.017, and that 46 I'll round to a 5, and that's our x squared coefficient, plus bx, so plus 1.9346. We had a 2 after that, and the 6 stays a 6. We'll attach our x, and then plus c, so plus a negative, we'll shorten that down to a minus. So then minus 25.3408. So if you want to see what this quadratic looks like, you can go into your y equals, key it in, again with the rounded to the 4 decimal places of accuracy. And I will key it in correctly there. There we go. All right. If you want to see your dots, turn your plot 1 to on. Second and stat plot, that's right above your y equals. Turn plot 1 to on, and we'll leave it on the dot mode. It'll default to list 1 and list 2 for your x and y respectively. That's what we'd like. And our window, 0 to 4 isn't going to do us much good on the x's. Our speed went from 30 to 70, so I'll maybe go 25 to 75 on the inputs. A scale of 5 should be sufficient there. Y min bottomed out at 18, so we'll drop maybe to 15. Topped out at 30, we'll go maybe a little above it. 35, counting by 5s is fine for that as well. And we'll hit graph. So there is our collection of points, and there's our curve sort of nicely going through our points here. So definitely a line would not help with this. If we looked at just this part, maybe we would think, okay, that could be linear, but no, in fact, speed and fuel usage have a quadratic relationship, not a linear one. All right, that should be enough to let you play with in section 3.4. So I would try 1 to 29 on the odds. And again, when you're looking to sketch a graph of these guys, you'll want to go 4 decimal places out. 2 decimal places, you'll see you actually end up missing your data. I can kind of show you that real quick just with the one we have here. If I only went 2 places out, I call this guy a 2 and cut the other 2 guys off. 9.3, that's a 4, cut those 2 guys off. 34, cut the other 2 guys off. And notice our curve then entirely misses the body of our points. All right, if you have questions, please get in touch. Otherwise, I'll see you next time.